Okay, there's a lot going on in these problems here in 5.6. They've given you a velocity function, and they're asking you to find really three different things. The first one they want is the displacement, and that one should be relatively straightforward because we've got a formula for displacement that should be in your 5.6 notes. Displacement is defined then, when you know your velocity function, as simply the definite integral from a to b of your v of t velocity function, taken with respect to time. So in this case, our a and b values here are going to be 0 and 10, and this is the velocity function that we're typing in. Now, we possibly could do this one by hand, but with the next thing we're going to need to do, that's going to be a calculator question anyway. So let's go ahead, and I think it would probably be worth our time to define that function here. So let's do that, and let's name it what it is, guys. If I can find v, which is always a little tricky right here. Might actually just need to go to the keyboard. Sorry. So let's do define v, except I don't want it to be uppercase right there. Okay, v. And now I think I can do the rest here. V of t, which should be hiding under the x right there, gotcha, is equal to... Okay, and our function there was, I better double check this in a minute, I thought it was a 36 minus a 24 and then a t... let me double check that now. 36 minus 24t plus 3t squared. Gotcha. Okay. 3t squared. Okay, there's your v of t function, so we'll define it that way. And now we just wanted to do, for displacement, the definite integral of that function on this interval right here from 0 to 10. So you guys are going to hit menu 43 here, go to your calculus menu, and do a definite integral. Again, we said from 0 up to 10. Gotcha. And then the v of t function, which, what have I learned right here? Oh, there we go. V of t. Okay, and all that was going to be taken with respect to t. Okay, and that's really all that we have to type in right there, and we end up with an answer of 160. I can't remember exactly what the units were on this problem, meters and then seconds there. So 160 meters is going to be our answer to this first question here of the displacement of the object. Now, as we're going to see in a few minutes right here, you got to make sure that you're interpreting displacement correctly. What that means is that during 10 seconds of travel right here, this object ends up 160 meters farther to the right than it was where it began. That doesn't necessarily mean, though, guys, that it just went 160 meters to the right, because this thing might be snaking back and forth a couple of times here. And all we're really doing here is comparing the location of the starting point to the location of the ending point. So the next two parts of this question are going to ask you to dig a little bit deeper into that. The second thing they want is total distance traveled. Now, this is another formula that was in your 5-6 notes. It's almost the exact same formula as displacement. The only difference is we apply an absolute value here around the v of t function in your integrand. Now that is probably, not necessarily, but probably going to give us a larger answer than this 160 meters that we came up with just a moment ago. So let me try this again, guys. Menu 43. All right, so an integral from 0 up to 10. And now what we need is the absolute value of v of t. And I think for me, I've got an absolute value button right there. You guys might have to look a little bit harder to get to that there. I always like to just type in ABS when I'm using my calculator there. Okay, so the integral of the absolute value of v of t taken with respect to t, and this one, yeah, like I thought, gets us a larger answer of 224. There's really no way this answer could be less than the 160 we came up with a second ago, and it will usually be more, 224 meters, and that's our answer for the total distance traveled, how far this particle actually moved on its trip from 0 to 10. And now the third thing they asked for, I always think I should put a problem like this in the notes, and I never do, so that's why you guys are always a little confused when we see it on homework right here, is asking us then to make this motion diagram here and show what this thing actually looks like during its journey. Now, to do that, what we're going to need to do first is figure out where the velocity of this object is positive and negative. So to do that, we're going to take the v of t function, 36 minus 24t plus 3t squared, and we're going to set that equal to 0. Now, this is a calculator question. You could just type this in, but I have a feeling this one isn't going to be all that hard to solve by hand. Could be wrong about that, but it looks like we could factor out a 3. And I tell you what, I'm going to reverse my order then and make this a t squared, and then a minus 8t and a plus 12 at the end of that when we factor out that 3. And I had a feeling that this quadratic is one that we'd be able to factor by hand. Let's see if I'm right here. This is going to be a t and a t. Signs look like they're going to be the same and both negative. So minus, minus. And I'm looking for two numbers that multiply to 12 and add up to 8. So that looks like it's going to be a 2 and a 6. All right, so we've got a 3-factored expression right now. We would set each one of them equal to 0 and solve, but of course there's no way that 3 can equal 0 because there's no variable there. Here, we're going to get t equals 2. That's the first time at which our velocity is equal to 0, meaning the object comes to rest. And then it looks like it happens again now at t equals 6. So these are the only two times that the velocity of this object here is going to equal 0. So what are we going to do with that? What that means, why is this not scrolling on me? Oh, maybe because I didn't do that. Okay, what that means then, guys, is that at every other time in this interval, the thing is moving. It's either moving to the left or to the right, depending on the sign of its velocity function. So this is something we haven't done much of since the end of the first semester. We picked some test values. I'm going to choose t equals 1 because that's less than 2. I'm going to pick t equals 4 right in between 2 and 6. And then I'm going to pick t equals 7. And I'm putting these test values into the velocity function. Now, we actually have 3 different variations here of the velocity function. Line 1, line 2, line 3, and definitely line 3, the fully factored version, is where we want to put these. You'll see why in a second. So, what happens to velocity at 1? The first factor here is positive, 1 minus 2 is negative, and 1 minus 6 is negative. Positive times negative is positive, which means the object is moving to the right on this interval from t equals 0 to t equals 2. Now, I wouldn't want to assume what's going to happen next, so we're going to test now v of 4. This term is positive. This factor, that's the word I should have used, factor is positive. This factor is negative. So positive times negative means that velocity is now negative, and sure enough, the object changed direction at t equals 2, and it's now moving back to the left. Now, I think I know what happens here, but again, let's test it. V of 7. Okay, this first term is still positive, times a positive, times another positive as well. So yep, it changed direction a second time and is now heading back to the right. So I now know that this object started off moving right, came back moving left, and then eventually ended up going to the right as well. But what I don't know yet, so this is not my answer right here, guys, is how far it moved right and left. It might actually have done something like this, right? And I don't really know. All right, so what we're going to do now is start breaking down the displacement of this function here a little bit and start finding it in pieces. The first thing I'm going to do is a displacement again, which we did earlier, is a definite integral of your velocity function, but now we're just going to go from 0 to 2 of the velocity function with respect to t. Now, since I know on this interval the object is moving only to the right, this answer is definitely going to be positive. I just don't know how positive it's going to be. So let me go back to my calculator, and one more time here, we will do a definite integral, got it, from 0 to 2, okay, of our velocity function here. So v of t, okay, taken with respect to t. Okay, survey says 32. So that tells us that this object has now moved 32 meters from the left to the right on the first leg of its journey. Now, the second thing we're going to need to do, how far did it move on the second leg of the journey, which starts at 2 and ends at 6. So this is a definite integral now from 2 to 6 of v of t dt. Now, what do we know? On this leg, the velocity is negative. So this displacement is definitely going to be negative when we type that one in. Maybe I can save a little time here if I just went and stole the last thing and just changed the limits of integration here. From 2 to 6, expecting a negative answer. Okay, now it's a coincidence. This won't always happen that these two answers were opposites of one another. That will not be the case. I didn't know that. I just knew that this had to be negative 32 meters. Now what that tells you guys is the displacement of this object from 0 to 6 would be 0. We moved 32 meters to the right and then back 32 meters again to the left. And I think I know the answer right here, but let's pretend we don't. The displacement now on the third and final leg of this journey, which is right here from 6 to 10, well, we know this is taking us to the right now. So this integral from 6 to 10 of v of t dt is definitely going to have to be positive. And I have a funny feeling that it's 160 meters if I'm remembering an earlier answer correctly. But let's pretend we didn't know that. Okay, so one more time, I'm going to steal my last integral right here, change that lower limit of integration to a 6, and that upper limit of integration to a 10. I hate being right all the time. And we got 160 meters for that third part. So now what they want us to do is put all of this together into what they call the motion diagram. So let's go ahead and do that. We now have all the information we need. We know how far this thing moved and how long it took to get there for leg 1 of this trip right here. So what happened, guys? It started off moving to the right, and I usually kind of curl it up like that at the end. And at this spot right here, this is what happens at t equals 2. That's how long it took to get there. And we know then that this distance right here, everybody, is 32 meters to the right from where we started, which of course we would call 0 meters. So it moved 32 meters to the right, and it took 2 seconds to get there. What does it do now? It reverses direction and goes right back to the exact same location where it started then. Now at that point right there, this is now at t equals, this upper limit of integration here was 6. And where are we at this point? Right back at the same 0 meter starting line where we began. And there's only one leg left of this journey, and it moves off to the right here, and it ends up 160 meters to the right of where we started. Now, I don't think I'm going to draw this to scale. 160 meters is 5 times 32, so this would go way the heck over here somewhere, and I don't think I have it drawn quite right, but that's okay. We would say this thing ends right here at t equals 10 seconds, and that this distance right here would be 160 meters, again, to the right of where we started. It might be kind of useful to think about, really, guys, this being a number line. Okay, moving horizontally right here with its origin right here at 0. And here we were at 32 meters, and then we end up there at 160 meters. So there's a lot of information that we were able to glean from this, this problem right here based on the velocity function. So kind of recapping, the overall displacement is 160, meaning we ended right here 160 meters further to the right than where we started. The total distance traveled, 224. What did we do, guys? We moved 32 meters to the right, 32 meters to the left, and then 160 meters to the right. Well, with total distance traveled, we don't care about negatives. So we would add 32 plus another 32 plus 160. That right there is a 64 plus 160 is going to be 224 total meters that this thing moved during its journey. And then we found out the individual displacements and drew this nice little motion diagram at the end to show us what was going on. So there's a lot of work involved in these problems, but we got a lot of information just based on that velocity function. So that's how you do those problems there in that section towards the beginning of 5.6.